observations. So they can be, although they may not have a significant role, like you cannot divide, if there are 10 authors, there is 10% to each. So it is not a really fixed rule, but some contribution the person has. So it still becomes difficult, but giving a name as an honorary author, that person has done nothing. If a person has just read your paper and give some critique, you can acknowledge in the thanks that I am thankful to such person for reviewing my paper. So acknowledgement is also important.
What about the lab manager?
The lab manager is just in charge of the lab.
Director.
No, lab director has no role.
His name is always there.
But this should not be.
Okay.
Should not be. The lab manager's name should not be. But lab manager is in charge.
Yeah.
Like for example, if I'm not saying don't understand
No, I know.
Garland. If Garland has made a lot of equipment for us, we always acknowledge in the acknowledgement section that the instrument, we had the help of Lloyd Sharp or Garland Sharp in designing and building this equipment, which is true. So one should acknowledge in some place the work. Many times you see papers published in crystal growth, and you see that in the crystal growth people obtain a crystal from somebody. Somebody grew in Germany a crystal for you and gave you a crystal, and then you do all the work on it. You measure properties and so on and so on.
Yeah, that's good.
And that person is not, many times that person is not an author.
They're not.
Pardon?
You said they're not an author?
They are not an author. They are just acknowledged in the acknowledgement that the crystal was kindly supplied by such and such person.
Yeah.
I am sure you have seen papers like that. I have seen lots of papers like that.
I don't think OSA allows more than 7. There is a rule.
There is a rule.
Yeah.
Yeah,
You put in optics letter.
Optics letters.
AOP,
Yeah.
maximum 7. It could not be. How come 3 pages
Yeah.
of paper have
Paper has-
17 minutes? That's good.
Yeah. So some journals are coming up with some rules. OSA published, I think I had a copy one time and I gave it to all the faculty. OSA published some guidelines, not the law or rule, but guidelines for authorship in research publications. So, okay? Now I'm going to, how is the time wise? Do you have a class or something? Can I take another 15?
Sure, yeah.
For this part, otherwise I can always skip this work on the crystal growth of the shuttle experiment. Now I'm going to talk a little bit about the experiment which we performed on the space shuttle mission. We had 2 experiments, one in 1985 on the space shuttle mission, which is called the Space Lab 3, and one in 1991 in the mission which was called the International Microgravity Laboratory. In both the experiments on crystal growth, Dr. Agarwal, who is sitting here, has a major contribution. We were all together in that experiment. It was all. So in those experiments, there is a diverse team of scientists and engineers who worked on it. And I don't have the list of all the people here. I have the list of major people here. Dr. Agarwal from A&M was heavily involved. Dr. Batra from A&M was very heavily involved. Dr. William Wilcox, who is the Dean of Engineering at Clarkson University in Potsdam, New York, was involved in the experiment because he did the theoretical calculation of the work which I did. We have James Stollinger from the Metro Laser Company in California, in Irvine, California. He was very heavily involved because he designed the optical system, holography system for this experiment. And Bruce Steiner, who is a scientist at the National Institute of Standards and Technology, NIST, which used to be the NBS, National Bureau of Standards, in Gettysburg, Maryland, was involved because we did some work on the beam line in Brookhaven National Lab to analyze this particular crystal which we do in the space. And then the space shuttle crew for the mission, I'm just mentioning here the IML mission, but the Space Lab 3 also was involved in it because they came to our lab here, they worked in this room, right across the room hall, to grow crystals, to work with us and to learn how to grow crystals and to understand the experiment. They stayed here for 4 or 5 days. During that time, all the crew members, 3 or 4 crew members, who did perform the experiment, so they were very involved. And there are many NASA scientists and engineers who supported our experiment during the mission, and they are in the order of hundreds. Because you need lot of help in a shuttle space experiment because the time is so short. If there is a problem, you need to solve it as soon as possible because the shuttle is flying for 7 days and you don't have a liberty that I'll go home and think about it and come back tomorrow. So if you have a problem, then you immediately put your thoughts together and you need all kinds of people, engineers, software engineers, electrical engineers, mechanical engineers, physicists, theorists, chemists, all kinds of people. So hundreds of people really work on an experiment. Even the building of the hardware for the crystal growth experiment was done by TRW, a company in Redondo Beach, California. And they had 100 people worked for 3 years to build this piece of hardware. Because it was very sophisticated, had lots of things which we told them as a scientific requirement and they built. So don't ask me the cost is in millions of dollars. I don't even know the exact cost, but it was in few $30-40 million of that kind. But, and there are many graduate students who worked on it in our organization. We grew crystal of a material called triglycine sulfate, which is in short called TGS. And this was grown, we grow in this lab. Some of you, if you go in the lab here, you see that we have lots of crystals sitting in the lab which are of this material. And this was grown by an instrument which was designed by us, built by TRW, called the fluid experiment system, which has crystal growth cell plus other diagnostic equipment in it to grow this. And we did do this experiment. One of the objectives was to perform holographic interferometric data to see that how the fluid behaves in the zero gravity, in the low gravity. So the fluid motion is determined using the holographic technique in this. We also studied the fluid motion and how the fluid is behaving by G-jitter. G-jitter means that during the shuttle mission, the astronauts perform various activities. They go on treadmill, they do other activities, they move from one place to another place, and because of that, the environment of the space shuttle changes. If the shuttle is flying at a constant altitude all the time, then the G levels are pretty constant. But shuttle doesn't fly at a constant altitude. They keep on changing the altitude and they perform it. Because of that, the G levels in the shuttle keep on changing, and that is called G-jitter. It's always like that. And we wanted to study that how the G-jitter affects the growth of the crystal. The crystal was grown by a technique which we designed in our lab here at A&M. It was grown by a low temperature solution crystal growth process using a cool distilling, and I will describe in a minute. And this was published a paper in '83. And this technique was especially suited for experiments in the low gravity environment. Crystals were grown on a oriented seat, this is a crystallographic orientation of a TGS crystal 010, and I'll show you it with the diagram. And this seed crystal was about 3.5 millimeter thickness. And the growth phase of this seed crystal was natural. Like if you have a crystal, for example, this is a crystal. When you cut a face, then it is not a natural face. But if this crystal is a polyhedral shaped crystal, which I'll show you in a minute, then if you don't cut this face, then it is a natural face and it has least defects. But as soon as you cut a crystal with a saw or a diamond saw, then it produces some defects of cutting, and that is not the best surface. The natural face is the best face. So we did grow on a natural face, and we used the undercooling, or what they call supersaturation, which means that, for example, if you take a sugar solution, you dissolve sugar in water and heat it up to make a clear solution. So if you dissolve it at a 45 degrees Celsius, it becomes clear. But if you cool it, then the sugar crystallizes. So the difference between the clear solution and the one where it crystallizes is a few degrees, and that's called intercooling. That is supersaturate by so many degrees, and then it crystal starts growing. So that is the point here. We studied the fluid motion. We put in the fluid where the crystal was growing particles of different sizes, 200 micron, 400 micron and 600 micron. And we tracked the motion of these particles in the fluid in the mission during the shuttle experiment by using holographic technique. And that gave us the fluid motion and how fast the fluid is moving in low gravity. Growth was monitored in real time. We are taking this data, optical data in the real time, and the particle motion was. People will say that why you want to go in macrogravity to grow crystals? And there are certain reasons. Why eliminate the buoyancy driven convection? Because on ground you have two things going on. You have gravity, always there, and then you have diffusion. Like if you heat a material or fluid moves because of the changing in temperature. So in space you don't have gravity. It is very low. And again the point is to make that the gravity is never zero. If somebody tells you that the space shuttle is flying in zero gravity, that is all wrong. It is not zero. It has a certain value. It can be 10 to the minus 6 g, or it can be 10 to the minus 5 g, or 10 to the minus 4 g's. But it is never zero. Zero means that I don't know what height shuttle will fly. It still will be some value, 10 to the minus 6 or whatever. So in a space environment, if you go do experiments of crystal growth, then we establish diffusion control condition. So diffusion is the only thing predominant there, and that we can control by changing the temperatures. And there is a transport phenomena, eliminates unwanted mixing. You cannot mix, like for example, if you take oil and liquid, oil and water together in space, they will be separated. But here on ground, sometimes they can mix because of convection and other things, but there is not. Eliminate sedimentation, the material doesn't sediment, and eliminated hydrostatic pressure, in a space. Liquid can be considered by surface tension, they can be contained by surface tension only. So that is a good place to study surface tension phenomenon. On ground it is very difficult, because there is other factors which are coming into the picture. And for many experiments, the low vacuum is an important thing, because outside the space shuttle the vacuum is almost 10 to the minus 14. So do a MBE in the space will be great.
Right.
And people tried it, I think, earlier. They tried to grow some films in a space shuttle experiment, because they were using this vacuum, they 10 to the minus 14 torr of vacuum. Clean vacuum, perfect. And why one should say that we will get a better crystal in space? The dielectric loss in TGS, the TGS crystal have a dielectric loss, and that is due to the following. Domain relaxation, because TGS has a domains, electrical domains. This is plus minus, just like like a dipole, and the domains are all relaxed. So if you somehow can make all this in one direction, then the crystal is a different situation, better. And these locations and the strain centers can be pinned to the domains. So that is the one reason. In space, due to the mainly diffusion controlled growth, we have ordered deposition. Deposition is much ordered of the crystal. When the crystal is growing on a surface, the molecules and atoms are attaching to the surface in a very controlled manner, because there is only diffusion there is no gravity.